Hi, I'm Oliver Jennrich. I'm the LISA study scientist with the European Space Agency, and together with my colleague Linda Mondin, who is the payload manager, I'd like to talk to you today about LISA, a mission to observe gravitational waves. How will this talk be structured? Well, we have about 30 minutes. The first half of the talk is given by me. I'll give you a little bit of an overview of how gravitational wave works, what the sources are, why are we doing LISA, not too much on the science because that's a vast topic and we are on a limited time here. Why do we need to go into space and how does the mission look like? And in the second half, Linda Mondin will then do the very difficult thing and tell us on how to we actually do LISA and what are the technical challenges and the technical solutions. So let's dive right in. I have to say, if you are an experienced person, then you might want to skip these next couple of slides. If you're new to the field and maybe watch this pre-recorded talk later, you might want to follow the next couple of slides so that you know what I'm talking about when I'm talking about gravitational waves. Now, what are gravitational waves? Gravitational waves are often described as ripples in space-time. They propagate with the speed of light. They come in two polarizations and they are transversal. So there are a lot of similarities to light, but there's one big difference. Gravitational waves change the distance between different points in space. So they are compatible with general relativity, so they're nothing new. Actually, they have been predicted by Einstein very early on when he formulated his theory of general relativity. Feynman and Mondin found later an argument why those gravitational waves are actually more than just a mathematical curiosity. They are carrying momentum and energy, so they are real. They are physical phenomena. And the first indirect detections was in the 70s when Hals and Taylor observed their now famous pulsar and observed a spin-up, and that spin-up was due to energy loss, which was beautifully matched by the energy loss predicted due to gravitational wave emission. The first detection, direct detection, was famously in 2015 with GW 150914 by LIGO. Now, what's the difficulties in detecting gravitational waves? Well, one thing is gravitational wave effects are tiny. They're really small. Typical effects of order 10 to the minus 21, so that's about the change of the distance to the sun by one hydrogen atom. So it's not much. So I told you gravitational wave change distances. So imagine a gravitational wave passing by here from the lower left to the upper right. And then let's look at this animation, and you see that gravitational waves stretch and squeeze the coordinate grid. And if the wave comes by a second time, we see that again it stretches this circle and it extends this circle. So here we see the spectrum of a gravitational wave, or the possible spectrum of gravitational waves, compared to the electromagnetic spectrum. We all know the electromagnetic spectrum is vast. It goes from long wave radio waves to high energetic gamma rays, or in terms of frequency, a couple of kilohertz to 10 to the 24 hertz. And squeezed in there is this tiny little sliver of visible light. Gravitational wave spectrum is similar. It extends also about 20 orders of magnitude from high kilohertz to very, very low frequencies. But there are sources everywhere, and we are trying to build detectors that capture a large enough fraction of that spectrum. Let's look at where our sources are. So I took the same spectrum as before, also marked with the time equivalence there from a few minutes to the age of the universe. And the far right we have supernova explosions, coalescing stellar mass black holes and neutron stars. These are the typical sources for LIGO, ground-based detectors. In a general rule, when we move towards the left in this diagram, we either increase in mass or we go to earlier stages of the same evolution of the object, or both. So our next lower frequency source are inspiraling compact objects. These are neutron star or small black holes, but not in the coalescing phase, but millions of years earlier. And also extreme mass ratio in spirals, tiny compact objects like white dwarfs, neutron stars, small black holes falling into supermassive black holes in the centers of the galaxies. These are very good in testing general relativity, as we will get a very specific signal that changes dramatically when the metric is slightly wrong, so to speak. Lower down, the in-spiral merger and ring down of supermassive black holes, so 10 to the 5 to 10 to the 9 solar masses. The object in our Milky Way has about 4 times 10 to the 6 solar masses, just for comparison. Depending on where you are in the mass range, anywhere between hundreds of years to hours. And then there is the last, or very low frequency source, which is the polarization of the gravitational, of the cosmic microwave background, which is a direct interaction between gravitational waves in the early phase of the universe and electromagnetic radiation. If you're long enough around, old enough, you will remember that there was a claim of the detection of that polarization a couple of years ago. Sadly, that turned out to be wrong, because it's a very difficult detection, because again, gravitational wave effects are tiny, and you have to make sure that all your other noise sources are well under control. Why are we not doing that with electromagnetic waves? I said we can detect extreme mass ratio in spirals, coalescing supermassive black holes. The thing is, gravitational waves carry information that you can't access with electromagnetic waves. Mostly because they are not absorbed by dust, so the universe is transparent, so you can see wherever you want. The signals are coming directly from the event horizon of a black hole, which is interesting because you can probe a spatial region that it's difficult to do that with electromagnetic observations. And you can test general relativity in extreme conditions. Of course, there's a considerable synergy with observation of electromagnetic counterparts. It's always good if you have more than one observation of the same source, you can learn more about that. So it's complementary to electromagnetic information, not replacing them. So here's the same picture as before, the same content, now just in frequency, sources, and also sensitivity of existing detectors. So this is where I plot where you can see in white the sensitivity curve of advanced LIGO, and you can see the two source classes I mentioned before, compact binary and spirals, core collapse supernovae, typically sources that you can see with LIGO, and there you see the beautiful trace of GW 150914, slightly louder than expected, but also a source, slightly unexpected source. So, but what you can see here, all those extreme mass ratio in spirals, earlier supernovae, you can't see with LIGO because LIGO isn't sensitive there. So what we want to have is a detector that opens up that low frequency window with LISA. So LISA sensitivity is anywhere between a hertz or so to down to 0.1 millihertz, which opens up the field for extreme mass ratio in spirals, the massive binaries, and also precursors of that one, because in an early stage of that one it would have been somewhere here. Now, why can't we do that on ground? Well, it's low frequency noise. What are low frequency noise sources? A lot of stuff that's going on at low frequencies happens because of us. Anthropogenic noise sources, people, traffic, industry, 10 Hz and below. And you saw the sensitivity of LIGO drops dramatically at about 10 Hz. Microseismic events like ocean waves and in general weird stuff. So This is one of my favorite cartoonists, the ex-KCD guy, and you can, the symptom he describes here is for real. There's a mysterious 20-second pulse coming from the coast of Africa somehow, and the reason is unclear, and it just highlights seismic at this frequency range is weird and very little understood, and a lot of sort of dragons lurk there. Clouds are a problem. They're overhead, not in the ground, but they are massive in terms of water vapor and in terms of their gravitational pull on your instrument. Even more massive, the effect of tides at about 1/10 of a millihertz, so typically 10,000 seconds, it's a couple of hours. That's the typical pattern of tides on Earth. And even more massive whole weather systems. This is a typical hurricane here, and the time scale there is about microhertz to 10 microhertz, so weeks to days. In any case, none of that you can get rid of. None of that can be shielded, and none of that can be you can be isolated from. So if you want to get rid of that noise, there's only one way to go. You have to go away from all that, get away from Earth. So the obvious solution then is go to space. Space has a big advantage. It allows for large distances. And I told you at the beginning, gravitational waves change distances. What I didn't tell you was that the size of that change, the amount of the change, is larger when the distances are larger. So it's a fractional change. So large distances correspond to larger signals. Vacuum comes for free, so you don't have to worry about particles getting in the way, but space is really, really hard, which means that you want to make the instrument as simple as possible. And if you're thinking about interferometric detection, as we always do these days when we do gravitational wave detection, because interferometric measurement of length is extremely precise, we typically have something like an L-shaped Michelson interferometer, like here on the left-hand side, with a beam splitter somewhere and two end mirrors, and then the light comes back and is detected. But if you go into space, you want to have everything as simple as possible. So you use 3 identical spacecraft where you put everything in: mirrors, beam splitters, and detectors. And then you can build 3 of them, which is much better than building 3 individual spacecraft. So having said that, you need 3 spacecraft. You are already convinced that you need to go to a triangle, and an equilateral triangle. Maybe where to put it? Well, you put them in a kind of cluster about 20 degrees behind the Earth, with distances between the spacecraft of about 2.5 million kilometers. 20 degrees here behind the Earth is about 50 million kilometers. Why do we do that? Because we want to reduce the influence of the Earth. So the further away you go from the Earth, the less the Earth matters in terms of pulling on the spacecraft and distorting the triangle. But you also want to be able to talk to your mission, because if it's too far away, then the bit rate drops down dramatically, or you need enormous antennas with enormous powers and all that. You want to avoid that on those satellites, plus it gets more expensive. So you find a compromise. The 2.5 million kilometers is kind of a compromise as well, but it's in the sweet spot of where you want to be in terms of sensitivity, in terms of frequency response of your detector. So it allows you to be large enough to get reasonable signals. So with 2.5 million kilometers, you're talking about a few tens of picometers for typical signals, and picometers changes are easily detectable. Plus, the orbit is still stable enough. The larger the triangle, the more unstable the orbit becomes. So that allows for about 5 years undisturbed mission duration. More if we want to. There is what you see there is also there is a little inclination of the constellation against the ecliptic, the 120 degrees there, or 60 degrees if you look at the normal vector, and that's just orbital mechanics. For some weird and wonderful reason, if you put spacecraft like that, they tend to stay with the same inter-spacecraft distance, with some variation. It's not perfect, but it's good enough. If you put that all together and follow the constellation throughout a year, because the orbit is about a year as you put it 1 AU away from the Sun, you see that the constellation rotates around the Sun, and if you follow an individual satellite like the blue one there, you see why, while the constellation total goes counterclockwise, around the Sun, the internal rotation is clockwise. So that is a consequence of this 60-degree tilt, and that it's open up to the top. It's not fundamental. There is a similar constellation that is shaped the other way around, where this tilt looks, opens to solar system south to the bottom. What are the drawbacks of that system? Well, standard interferometry is not possible. The spacecraft are moving. They are not perfectly at the same position. The distance between the spacecraft changes, so you get a Doppler effect. So at the end, you have to concede that you can't do homodyne interferometry, but heterodyne interferometry, which is less sensitive, but sensitive enough for our purposes. The direct reflection of light, like having a good old mirror there and hit the mirror with some light and get it back, is impossible. The laser beams open up to many kilometers. You receive the light through a small telescope, and so you're not getting enough light, and doing that twice leaves you with a few photons per second, which is clearly not enough. So we borrowed a transponder scheme from radio astronomy, or general radio link or radio communication to satellites, and Linda will address that in more detail, but that allows us essentially to run individual lasers on each satellite, just sending out light and receiving light from the other satellite. And the last thing is that our reference points are now in free fall, so you don't have mirrors at the end. You have reference points to which you measure the distance. They don't have to be in free fall, strictly speaking, but you need to know the non-gravitational forces to about 10 to the minus 15 meters per second squared and root hertz. And it turns out the best way of doing that is, instead of picking any old number, pick 0 and put them into free fall, which means no external or no non-gravitational accelerations. That has been demonstrated by a mission called LISA Pathfinder that ESA and NASA together operated in 2015 to 2017. So, I gave you a number of problems. How to solve these problems, I hand off to Linda Mondin, who will tell you all and maybe more than you want to know about the technical solutions and difficulties in LISA. Thanks.
Thank you, Oliver, for the introduction, and welcome everybody to this exciting session on how do we do LISA. I'm Linda Mondin. I work on the payload at ESA, and LISA is an extremely complex mission, very much work in progress, which is work of a lifetime. I myself have been working on it since the early 2000s with my master and PhD thesis, and I expect to still be there around lunchtime in the 2030s. As Oliver has already mentioned, ground space antenna work on the principle of interferometry. The light is split in two, goes towards the end mirrors, and when it comes back, it interferes destructively when the arm lengths are exactly equal, and when those arm lengths vary, then we see light in the detection arm. Now, as Oliver has also mentioned, we are limited at low frequency by seismic vibration and the arm length. If we go onward and we'll look at what we go when we try to take LIGO to space? Well, we build the antenna, we would have to bring it to space, and we would need to make it bigger. We would change its name, of course, call it LISA. And please take into account that the scale here is nothing whatsoever on scale, actually, between the LIGO and the LISA. And basically what we would have to do is build one spacecraft, which would have to host the source, the splitter, and the detection, and one spacecraft each for each of the end mirrors, which basically means we would need 3 spacecrafts. And if we need to have 3 spacecrafts for standard Michelsons, which are 2 different types of spacecrafts, basically we need to make one first statement is that oftentimes recurrent costs are less important than doing a new development. So it's generally not a bad idea to make spacecrafts identical. If we were to look at an interferometric configuration with 2 arms versus 3 arms, then the 3 arms would have advantages. Basically, we would have 2 partially correlated Michelson and a Sagnac configuration, and we would be sensitive to the polarization of gravitational wave signals. So there are arguments to say that 3 arms may be better than 2. The arm length, as we've seen, is dependent on the frequency of the gravitational waves, and the sweet spot seems to be those 2.5 million kilometers, as Oliver was mentioning. And the important matter here is to keep in mind that this 2.5 million kilometers is not a set length, but we are subject to orbital dynamics. And if we look at how much light is available at the distant spacecraft, as Oliver has already mentioned, even if we were to take a very, very large mirror for a space one, which is, say, 1.5 millimeters, then we would have to still have a very large laser power. And in the case of a one-way link budget, we would have still a very, very vanishingly small amount of light coming back from the second spacecraft. So if we were to make it more reasonable so that we could have actually 2 such telescopes on board of a single spacecraft, like say 30 centimeters diameter, and more reasonable so in terms of amount of light emitted over the long lifetime, a couple of watts, then definitely this becomes absolutely impossible, and therefore we have to go to a transporter configuration, as already mentioned. And so we are coming to a 3 spacecraft in an equilateral triangle, 2.5 million kilometers away, connected by the laser link. And if we look at the gravitational wave strain, typically this will change the length of the arms by something of the order of a picometer, which if we scale it to the distance from here to Proxima Centauri is roughly the thickness of a piece of paper, not very large therefore. So measuring the distance is, however, the easy part, because it's the distance between what we have to measure. Well, we want to measure the distance between free-falling test masses. And those free-falling test masses we have to insulate from any force which may be acting onto it. For example, it may be from collisions, which would change their positions. And therefore, the spacecraft has to have as a shield, and if we go into more detail, it has to be a shield, but it also has not to perturb the test mass. So it has to ensure that it is moving around this test mass with a drag-free motion using micronewton thrusters. It has to ensure that we have a gravity balancing on board of a spacecraft so that gravitational forces are not exerted on the test masses, especially varying gravitational forces. Also, electromagnetic forces have to be controlled, therefore we're allowed only small magnetic fields, and the test mass has to be discharged. And as already mentioned, of course, collisions, no go. All of this was actually demonstrated on LISA Pathfinder, and I'll give you a little more detail in the coming slides. So as we mentioned, we have to measure distance at 1 picometer level over 2.5 million kilometers in the frequency range. And this implies that we have to have a bit node of a distant spacecraft laser light with a local oscillator. And if you were to measure 1 picometer over 2.5 million kilometers, then the laser frequency would have to be stable in a one-way link to something of the order of 10 to minus 19, which is just not happening ever. Ever, actually, yes, not even in the future. We have physical limitations which may be coming into play when we talk about those frequency stabilities. In a Michelson configuration, the laser frequency noise cancels out as long as the interferometer arms are equal, which in LISA, as we've mentioned, they are not. However, we can make them be equal by appropriately delaying and adjusting the one-way links which we are recruiting from the antenna. So what was LISA Pathfinder? It was a demonstrator mission which was designed to test the critical technologies for LISA. It was launched in December 2015 and reached roughly 6 months afterwards its orbit around the L1 Lagrange point 1 between the Earth and the Sun. It was able to demonstrate satisfactorily free-falling task masses, the picometer resolution displacement sensing, the drag-free control, and the micronewton proportional thruster systems. And if we go into more detail, what was obtained was that over the most quiet periods in the runs around April 2016 and around December 2016 even more so, towards the end of its lifetime, when the vacuum inside the housing of the gravitational reference sensor head was the best, it greatly exceeded the requirements of LPF and actually demonstrated the LISA requirements altogether in the low frequency region of a spectrum. This was extremely powerful verification. So from this preliminary initial configuration, we come to 3 identical spacecraft, 3 interferometric arms, that is to say 6 one-way links, 4 one-way links per spacecraft, with the laser power being regenerated in the transponder configuration, and recombination of the different arm measurements with appropriate delays aligned for the chosen interferometric configuration. The gravitational reference system will be built as per LISA Pathfinder. As we saw, it was perfectly satisfactory. So if we look at the sensitivity curve of LISA, and we have it here as Oliver has already shown in much greater detail, that in the central part of the spectrum and in the high part of the spectrum, they are essentially limited by the interferometry and displacement sensing noise and the arm length penalty at higher frequency, and in the low frequency spectrum, they are limited by the test max acceleration noise, which was fully demonstrated by LISA Pathfinder. As the relevant measurement involves the relative motion between the test masses 2.5 million kilometers apart, this involves the usage of different interferometers on board of each spacecraft: test mass interferometers, reference interferometers, and science interferometers. More on this on the next slide. The need to have a single stable laser source over the constellation is satisfied by offset frequency phase locking all transponders laser to the constellation master laser. The constellation master laser requires having a stability of 10 to minus 13, which is significantly less constraining than the 10 to minus 19 needed for the single length measurement, and which is reachable with current technology. The spacecraft relative velocities are different for each spacecraft couple and variable over time. The Doppler effects are typically between plus or minus 8 MHz. The frequency of a bit nose is therefore link dependent and changing over time. The heterodyne bit node is cut between 6 and 25 MHz, 25 MHz being the phase meter bandwidth, and 6 MHz being a frequency ensuring that the measurement is shot noise limited. Time delay interferometry also requires a combination of data streams from a free spacecraft, which implies that the local oscillators have to be stable, where jitter from one spacecraft to the other have to be known, and the cancellation time has to be known with a very good precision. Also, this cancellation time has to be related with an absolute time. The knowledge of arm lengths to sub-meter accuracy is also needed. Modulation of the lasers from the phase meter are provided in order to satisfy these requirements. A pilot tone modulation with a frequency change of 1 MHz between the clockwise and the counterclockwise frequency is needed. And the pseudo-random nose code modulation using the LVDS protocol is also needed for arm length and timing. This PRN code modulation allows for data transfer capability free of charge on the optical link, with a data transfer rate of the order of kilobit per second. On this slide, more details on the measurement schemes. Please bear with me for a second, as I will need a laser pointer for this one. As you can see here, you have two identical optical benches per spacecraft. On each identical optical benches, we will have a science reference and a test mass interferometer. On the science interferometer, the light coming from the distant spacecraft will be mingled with the light coming from the local laser. Then on the reference interferometer, the laser on the optical bench will be mingled with the laser coming from the other optical bench via the backlink. Finally, the local laser from the other optical bench via the backlink, having been reflected back from the test mass, will be mingled with a loop. A few other design constraints have to be approached carefully. First and foremost, the constellation breathing angle. As the arm length will undergo yearly variation, the constellation angle between the two links on each spacecraft will change by plus or minus 1 degree. Such a variation, if uncorrected, would drop the laser links. Two options have been assessed: telescope pointing and infant pointing. The preferred one has been the moving optical subassembly, which is to say, the optical bench, telescope, and test mass on each arm being moved solidarly with respect to the other arm. The infant pointing was found to have a requirement of a first beam expander, a mirror allowing for the pointing, and the second beam expander, which would have made the optical design slightly more complicated. Additionally, it would have resulted in increased cross-coupling from spacecraft translation and would have required enhanced test mass readout in the y direction. The moving optical subassembly has its own difficulties nonetheless. The two test masses for spacecraft are present, the mechanism and the pivot point are critical, and the performances of a fiber backlink, especially as it pertains to fiber backscattered, are critical. On a good news, we have now gamma radiation tested the candidate fibers, and they have passed the test. The data transfer to Earth is also not a trivial point. Downloading from each spacecraft separately is problematic, as the ground station would have to point 3 times. Also, antenna motions on each spacecraft on a weekly timescale would have to be accounted for. The data transfer coming from a constellation is found to be more favorable. The capability of transferring via optical link all data to a single download spacecraft is possible and inherently present, and would be possible even with a loss of one link. Therefore, downloading all data from a single spacecraft is the preferred option. Secondly, if we were to shoot our laser at the location of a distant spacecraft, after it will have moved in the time taken for light to reach it, we would then miss it. So we have to point ahead the transmit laser. This angle is relatively constant in the plane of a constellation and is equal to 1.7 microradians in free space. But out of plane, this is changing over plus or minus 3 microradian and has to be corrected. This implies the presence of a mechanism on the optical bench, whose performances are not trivial. Nonetheless, a demonstrator has already been built. On this slide, the high-level physical architecture of the payload on board of each spacecraft. You will see that we have a LISA core assembly including two MOSAs, including in return a MOSA superstructure, the telescope, the optical bench, including the constellation acquisition sensor and the quadrant photoreceiver systems, as well as the GRS head, the support of the MOSAs, their shielding, electronics, and actuation. Then there is the laser system, including two laser assemblies, one of which is interfaces with a laser pre-frequency stabilization and has got master capabilities, the other being able only to be a transponder. Two phase meters, frequency distribution system, signal conditioning, laser assembly control, and quadrant photoreceiver power supply. Finally, a gravitational reference system, including cage inventing, grabbing, position and release mechanism, control units, charge management system, GRS front electronic, and the GRS head. Harness, instrument control computer. A few problem areas have been identified. First and foremost, acquiring the laser links once the spacecraft have reached station. Usually, acquisition is commanded via ground. The lag time in the case of LISA makes this unfeasible. An automated procedure between the different spacecraft is therefore necessary and challenging. Another point is that maintenance will be, simply put, not be possible. As such, lifetime has to be guaranteed with the units which will be available from ground. Lastly, several key requirements give rise to draconian cleanliness needs. More on this in the coming slides. Finding the distant spacecraft laser signal will not be trivial, the main limit being the uncertainty of a line of sight between the telescope and the star tracker. The very small field of view of the science detectors will also not be ideal, as will be the fact that on the science detector the signal will only be visible if a bit note is within the phase meter bandwidth, that is to say, if the local and the distant laser will be a maximum of 25 MHz apart. As such, a large field of view detector, the constellation acquisition sensor, is implemented. It is used to calibrate the line of sight of a telescope with respect to the star tracker by looking at stars. It is also used to find the distant laser beam and bring the laser light on the science detector in the location which corresponds to the quadrant photoreceiver and keep it there. This hinges on two assumptions: that the transmit laser stray light is not flooding out the detector too badly, and that attitude control capabilities on the constellation acquisition sensor are possible. Both of these are to be consolidated. Lastly, once that attitude control capability were to be reached, laser frequency dithering would bring about the reaching of a science mode. As mentioned, LISA is the work of a lifetime, and its lifetime is under discussion. We are looking at a minimum of 12 years of lifetime for each unit, which is then broken down as shown here under. The components will have to be procured much earlier in bulk to deal with obsolescence. As such, the qualification duration and the cost will be very significant. This long lifetime has implications and forces us to look into redundancy schemes and their optimization. Cleanliness is a major concern, most specifically the vacuum quality inside the GRS head, which has to be better than micropascal. Three options have been studied: pumping, which has been considered as non-optimal due to microvibration, magnetic and electric fields, and long lifetime of emission; early venting, which, on the other hand, requires a change to existent mechanism and is such not a preferred option; and finally, reducing the molecular contamination, especially the water content, inside the venting tube by keeping it sealed and pumped on ground. The vacuum quality requirements are similar for the laser pre-stabilization system, but are less critical. As such, pumping or early venting are also under consideration. To reduce the particulate contribution to the backscattered coming from the local laser on the constellation acquisition sensor, a cleanliness level 500 or better has to be maintained throughout the mission. In order to reduce wavefront deformation, laser-induced contamination, if present, has to be mastered. The molecular contamination deposit, which could modify the wavefront as shown in the picture here, has to be maintained below a few nanometers. Lastly, lack of cleanliness could bring about catastrophic optical damage, which could easily spell an end of a mission and has to be avoided at all costs. In summary, the Phase A design consolidation and iterations are ongoing, and no showstoppers have been identified. The technological development activities for critical subsystems are largely in place or planned, and the TRL-6 demonstrators are on track for adoption. The Phase A extension will start towards the end of October this year, with 2 parallel contracts, including the instrument under prime leadership. I would like to thank you all for your attention and apologize for the lack of a video